Dream to become the next Sir Isaac Newton or Albert Einstein? Learn calculus from Refat Bari, aka 800 over 800 guy, is teaching calculus this year. Watch his videos.
Hello folks, this is Refat Albert Bari from Bioscience. Today we're going to be talking about derivatives for the first time. What are derivatives, you might ask? Well, derivatives are almost like limits, right? And to get an introduction to one of the derivative rules, we're going to be taking a look at this question. Let f of x equal x to the power of n. So what is the derivative of f of x? So when I say what is the derivative of f of x, which can also be written as what is d over dx of f of x, which can also be written as d over dx of x to the n. What I really mean is I want to take the limit of x to the n, or f of x, whichever way you want it, as h approaches 0. So how do we do that? Well, it turns out that to solve any limit, really, what we're going to do is use the limit definition of a derivative, right? And what is that definition? Well, if you remember, it's f of x plus h minus f of x over h. So you probably recognize this, right? This is the same equation we use to find the slope of the tangent line. And that's because that's what a derivative is. We're finding the slope of the tangent line of this function. So how do we do that? Well, what is f of x plus h in this case? Well, f of x here is x to the n. So f of x plus h is simply going to be x plus h to the n, right? Pretty simple. What about f of x? That's just x to the n, all over h. Now this is where things might get a little bit complicated, so follow along closely. This is of course a binomial, right? X plus h to the n. How do we expand this binomial? Well, in your elementary school, you probably remember x plus y squared is equal to x squared plus 2xy plus y squared. But given that x plus y squared is this, how do you find out what x plus y to the 5 is? X plus y to the 7, and x plus y to the n ultimately. Well, to figure out the binomial coefficients, what we're going to use is something called Pascal's triangle. Now, Pascal's triangle is a very nice geometric way to take a look at some counting problems. So let me show you what Pascal's triangle looks like. You have a triangle made up of the sum of the previous numbers. So 1 plus 1 was going to give me 2. And that 2 is surrounded by 1s. 1 plus 2 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And so on and so forth. So if you notice, each row of the Pascal's triangle is going to give us the binomial coefficients of any binomial expression. Now you're probably thinking, what do I mean? Well, let me show you what I mean. Let's break this triangle up into its rows. Right, this is row number 0, row number 1, 2, 3, 4. So let's say I want to find a binomial expansion for x plus y squared. Well, I'm going to take a look at the second row of the Pascal's triangle. Looking at the second row, I see that my first binomial coefficient is going to be 1. So I'm going to write 1. Then I'm going to take x and square it. And y is simply going to be 0. What about my second binomial coefficient? That's 2. So I'm going to take 2. I'm going to decrease the exponent of x by 1 and increase the exponent of y by 1. And for my final term, I have my last binomial coefficient as 1. Once again, I'm going to decrease my exponent here to 0 and increase my exponent here to 2. Once you simplify that, you get the classic x squared plus 2xy plus y squared. Right? That's pretty simple. And let's do one more, just just for the sake of understanding, if I want to find the binomial expansion for say x plus y to the, I don't know, 4, I'm going to look at the fourth row of the Pascal triangle. To get my first binomial coefficient, I look at the first term in my fourth row. So, and that's 1. So let's put down 1, and I'm going to maximize the power of my x variable and minimize the power of my y variable. And now I'm going to start decreasing my exponent. I'm going to start decreasing the power to which x is raised and start increasing the power to which y is raised. So let me show you what I mean. The next coefficient is 4. This is going to become 3. This is going to become 1. Next coefficient 6. This is going to become 2. This becomes 2. Next coefficient is 4. This becomes 1. This becomes 3. And last term is last coefficient is 1. This becomes this one becomes 0. This becomes 4. And if we simplify that, we get x to the 4th plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the 4th. So now I hope you have a general understanding of why Pascal's triangle is so useful and how it can help us expand binomial expressions. But the problem is we're trying to evaluate x plus h to the nth power. We don't know what n is, right? It's generalized. So how do we find the binomial coefficients for the nth row of the Pascal triangle? Well, it turns out if you zoom out and kind of go to the nth row of the Pascal triangle, you're going to see a bunch of combinations happening here. So what do I mean by that? Well, the first term, the first coefficient is simply going to be, is going to be n choose 0, because we're taking a look at the 0th coefficient of the nth row. Our second coefficient is going to be n choose 1, because we're looking at the first coefficient of the nth row. And so on and so forth until you reach n choose n minus 1 and n choose n. Right? And that's in essence how you get the binomial coefficients for the nth row of the Pascal triangle. So how can we use that to our advantage? How can we use that to expand x plus h to the n? Well, first let me erase all of this. I don't need it anymore. So, okay. So here I have x plus h to the n, and my goal is to expand this. First thing I'm going to do is I'm going to take a look at the first binomial coefficient of the nth row, and that's n choose 0. Of course, we know that anything choose 0 is simply going to be 1, but we'll simplify it later. Now I'm going to maximize the power of my x variable and minimize the power of my h variable, right? Plus my second binomial coefficient is n choose 1, right? And of course that will simplify to n. We'll do the simplification later on. And I'm going to decrease my power by 1 for x and increase my power by 1 for h. Now let's look at the third binomial coefficient, n choose 2. And you get the flow, right? And I can keep going on and on like this. But the matter of fact is we can just skip ahead to the last few terms, right? My second to last coefficient is going to be n choose n minus 1 of x. So that, what is it? X to the n minus 1, h to the n. And my absolutely last term is going to be n choose n. And of course, there's only one way to choose n things from n things. X to the 0. And h to the what? Sorry, this is h to the n. And this should be n minus 1. Okay. So we've expanded x plus h to the n. Now how do we simplify it? Well, you can go ahead and simplify the first and last few terms. You know that n choose 0, anything choose 0 is simply going to be 1. So we can just write 1 times x to the n h to the 0 plus. Anything choose 1 is simply that anything. So that's going to simplify to n times x to the n minus 1 times h plus. N choose 2, you get the pattern, right? We can, let's just keep it like that and not expand it. Okay, n choose n minus 1. N minus 1 is just going to be what? 1. And times x times h to the n minus 1 plus n choose n is just 1. X to the 0 h to the n. We're almost done. Let's simplify it even more. Let's just take out these ones. And that's the rest of the simplification really. And we're done, right? We're done simplifying and expanding x plus h to the n. So now what do we do? Well, now we can just plug in this expansion back into our original expression, right? So as you can see, we have x plus h to the n minus x to the n. So I'm going to take all of this. And subtract x to the n from it. Because remember, we can't forget about that outlier minus x to the n. And of course, we divide all of that by h. Because we're finding the limit of this expression as h approaches 0. Okay, we are almost halfway done. So if you remember, our goal was to find the derivative of f of x, where f of x equals x to the n. And yeah, our goal is to derive the power rule using the limit definition of a derivative. And we're almost there. So let's bring over this expression over here. So what do I have? I have the limit as h approaches 0 of x to the n plus nx to the n minus 1 times h plus n choose 2 x to the n minus 2 h squared all the way to the last few terms, n choose n minus 1 to the times x times h to the n minus 1 plus h to the n minus x to the n all over h. Okay, immediately you see something that cancels out. X to the n, x to the n. Alright, we've made our job at least a little bit easier. Now you notice that, like most derivatives, you're going to try to factor out an h somewhere. And you can see all of these terms have h's. So let's do that. Let's factor out that h. So the limit as h approaches 0, let's factor out that h so that we get n times x to the n minus 1. Now this h is gone, right? And now all my h's will have one less for their power than they used to have. So now I'm going to have n choose 2 x n minus 2. And now instead of 2, my h is going to be the power of 1. And if you apply that that understanding to all the other powers of h, you'll recognize that this second to last h will now have an exponent of n minus 2. Because I just factored out that h. And of course my last h will have a power of n minus 1 instead of n. Okay, now I'm almost done. As you can see, because I factored out an h on the numerator, I can cancel it with the h in my denominator. Boom. Right, now what am I left with? I have to find the limit as h approaches 0 of this massive monster. N times x to the n minus 1 plus n choose 2 x to the n minus 2 times h plus all the way to the last few terms n choose n minus 1 of x times h to the power of n minus 2 plus h to the n minus 1. Now as you can see, this is where all of our simplification comes in handy. H approaches 0. Anything multiplied by 0 is just 0. That means all the terms that are multiplied by h will be reduced to 0. All of this 0. So that means our final answer is nx to the n minus 1, which is the derivative of our original function f of x. So we can thus conclude that the d over dx of f of x, where f of x is x to the n, is n times x to the n minus 1. And that, folks, is what we call the power rule of derivatives. So thank you for watching, and we'll see you next time.
To fall in love with math and science, especially programming.